So here's an example to do with lines parallel to the sides of a triangle. Okay, so here's a triangle ABC with a line DE parallel to BC there, and it cuts it into 8, 4, and the whole value of AC is 9. And we're looking to find this AE here. Well, let's look at the possible ratios we can use. We can look at AD over DB equals AE over EC, or we can look at AB over AD over AC is equal to AC over AE, or we can go at all of AB over DB is all of AC over EC. Okay, so we'll go with AB over AD equals AC over AE, because we know 3 of those. We're looking for AE. Plug those values in, AB, AD, and AC, and cross multiply. 12AE equals 9 by 8, so AE is equal to divide both sides by 12. 72 divided by 12 is equal to 6. Now let's look at angles and circles. We'll move away from angles and triangles for a little bit, even though we'll come back to them. So just remind ourselves, all the way around the circle is the circumference. Across the circle through the center point, through the center of the circle is the diameter. From the center to the circle is the radius. This part of the circle is a semicircle. This line that touches two sides, two parts of the circle is known as a chord. This part here is not a semicircle, it's a segment. This part here is a sector of a circle, and this part here on the circle is known as the arc. And then we can also say that the angle in a semicircle, which we'll look at in a second, sorry. If we have a triangle in a circle with its base as the diameter, then the point where the triangle touches the circle, at that point, at that vertex, that is a right angle. It's 90 degrees, okay? And this is also known as the angle in a semicircle. That's where it is. There's the triangle. It's at this point where the triangle touches the circle. That's the angle in the semicircle. Now, sorry, just my attention is brought back to the converse of the previous theorem about lines parallel to the sides of a triangle. I'll just dip back there for a second. If a line cuts two sides of a triangle in the same ratio, then that line is parallel to the side of that triangle. So it's just the converse of that other theorem. Okay, let's look at the angle in a semicircle. Here we go. Here's a circle. Here's a line through the diameter. Here is a triangle formed, and where the vertex of the triangle touches the circle, the angle in the semicircle is a right angle. It's always 90 degrees. Okay, so if I go like this, this angle is always 90 degrees. So however I draw it, that's always 90 degrees. So let's look at an example. A, B, and C are 3 points on a circle with center O. Okay, so there is our triangle ABC. Oh, sorry, 3 points that form a triangle. Okay, now a center O, and this angle is 65, and this angle is X. And we're asked to find the angle OBC. We're asked to find that angle in there. Okay, so that'd be easier if we do this. So we're asked to find this angle in here, okay, OBC. Now the important thing about these problems is that it's always, and it often comes up, is that you should always identify the fact that there's an isosceles triangle in here, or whether it's one. There's one here, okay. Why is there one here? There's two here actually. We have a triangle in here, okay, OBC, and this side is equal to that side because they're both radius of the bigger circle. And we have a triangle here as well, and this is a radius and that's a radius, so that's an isosceles triangle and that's an isosceles triangle, and that's very important in finding the solution to these problems is to identify the fact that there's an isosceles triangle there, generally borne out the fact that the lines drawn from the centre to the circle are the radius, and if there's two of them, that they're equal in length because the radius is the same all the way around. Okay, so to do the solution and to find the angle OBC. Triangle OBC is isosceles since OC is equal to OB, which I've just drawn there. OC is equal to OB. Okay. Therefore, the angle OBC, this angle, must be equal to OCB, that angle. Why is that? Because if you remember from a few chapters ago, in an isosceles triangle, angles opposite the equal sides are also equal to each other. So this is opposite a side which is equal in length to this side, so the angle opposite that length, these two angles are equal. Okay, angles opposite equal sides are equal in an isosceles triangle. So 65 degrees is the answer to that. And then if we're looking to find, so we have this is 65, so now we're looking to find the angle AOB, which is in here, okay, part 2. So the angle BOC, this angle BOC must be equal to 180 minus these two 65s, okay? So this angle in here, it's not, don't assume it's 90 degrees. Don't assume that, okay? It's actually equal to, because in this triangle you have this angle plus this angle equals 180. It's actually equal to 50 degrees, okay? Angle BOC. And if that's the case, then this angle here is 50 degrees. Then the angle AOB, this angle here, must be equal to 180 minus 50 because this is a straight line angle, isn't it? So if one is 50, this is 180. So that's equal to 130 degrees. Okay, and then finally we're asked to find the angle OBA, and so again in that smaller triangle, if I can just bring it down here again so I can see it at least. Okay, well, we'll just go with it. Again, in the smaller triangle, OA is OB because they're both radius here again, and therefore the angles opposite those equal sides must be the same. They're both x, okay? And we know the sum of the angles in a triangle x plus 130, because we worked out that was 130 earlier, is 180. So 2x is equal to 50. X must be equal to 25. So the angle OBA, this is 25. And x is 25 as well. Now, let's consider the angle at the centre of a circle and the angle at the circumference. So if we look at this diagram here, angle ACB is at the circumference of the circle standing on this arc AB. Okay, and the angle AOB is the angle at the centre of the circle that's also standing on the arc AB. Okay, so we have a theorem here that says that the angle subtended at the centre of the circle is twice the angle at the circumference. So it's saying that this angle is twice that angle. Okay, AOB is twice ACB. And there's a corollary to this, and that's basically saying that it must follow on, or it must be obvious that the corollary from a theorem means, if we've stated something, then it should also kind of be obvious that the angles in the same segment are equal. So here's an example here. It's saying that this angle x is equal to that angle y. Okay, and that kind of makes sense really, because if you think about it, this is twice this, and this is twice that from above, so this must be equal to that. Let's talk about cyclic quadrilaterals, and basically A cyclic quad is where all the vertices are on the circle. So there they are, they're all touching the circle, or on the circle. And we have another corollary that says that the opposite angles of a cyclic quad add up to 180. So A and B add up to 180. Okay, and basically, if you think about this again, this is using this. It is a corollary to this theorem, believe it or not, even if it doesn't look like it. But this angle here is twice that angle, and this angle is twice this angle. This is 180. Okay, and you know that 180. So this is 180. That 180 is equal to 2x, and this 180 is equal to 2y. So 2x plus 2y must be equal to 360. So x plus y is equal to 180, which is the proof of that. Corollary 3, the angle in a semicircle is a right angle, and we mentioned that earlier, and the fact is that this angle at the centre of the circle is twice this angle. So this is 180, it's a straight line angle, so that must be 90. Okay, here's an example. In the given diagram, O is the centre of the circle. That's here, it's not there, but it's now. The centre of the circle, find A and B. So we find this angle, and we have to find this angle. The angle on the circumference and the angle at the centre of the circle. So we know that this is 48. So if this is 48, then this A must be 48 as well, because they're both, B is twice 48 and B is twice A, so A must be 48 as well. And the angle B then is twice this, so the angle B is 96. Now, example 2, find the angle ACB and the angle ADB. So ACB, ADB. Okay, so the angle ACB, well, that's straightforward enough. That's half of the angle AOB at the centre. It's 40 degrees. The angle ADB, now we have to consider the fact that we have a cyclic quad here. Okay, so the angle ADB plus the opposite angle from this corollary here must be equal to 180. So ADB plus 40 is 180. ADB is 140. And here's a third example. Okay, let's make it bigger. Okay, so find the angle ACB. Okay, well, that's straightforward enough. That's half of that, it's 55 degrees. Find the angle OAC. OAC, find this angle here. Okay, so how do we solve this? Well, to find that, what we've done is we've actually done a construction and we've joined C to O. Okay, you can see C to O is joined there. Okay, and that creates an isosceles triangle because we have this side equal to this side. That's 30 degrees. That's opposite this side. So the angle opposite the other equal side, this must be 30 degrees here. Okay, so that's 30 degrees. So the angle ACB is equal to 55, because we found that earlier here. Okay, it's equal to 55, and this is equal to 30. So this angle in here then must be equal to 25 degrees, because 55 minus 30 is equal to 25 degrees. And if that's the case, this is the radius of a circle, this is the radius of a circle, this angle of 25 must be equal to this angle of 25 as well, which is what we're looking for, because again of the isosceles triangle and using the radius being equal.